Hello, and thank you for watching my video on learning assignment order in an Ant Colony Optimiser for the University Course Timetabling problem, or UCTP. Now, this is a combinatorial optimization problem which is known to be computationally hard. We are using the International Timetabling Competition 2007 benchmark and formulation. To create a feasible timetable, we must assign a series of course lectures to rooms and time periods in such a way that none of 5 hard constraints are violated. We are also given 4 soft constraints, and it is a weighted sum of these violations that provides our single objective to minimize. Ant Colony Optimisers, or ACOs, have shown moderate success in timetabling tasks, but have generally not achieved the level of results that some other meta-heuristic or hybrid methods have. ACOs construct solutions sequentially, meaning that some ordering of the lecture assignments is required. Our motivation in this study is to investigate how, if at all, this ordering affects average solution quality and whether we can learn what makes a good permutation in larger problems. We develop a max-min ant system, or MMAS, with an edgeless construction graph. Nodes are arranged as a 3D matrix such that each node encodes a distinct placing of a lecture to a time period and room. The illustration shows an ant part-way through constructing a solution. Unavailable placements are shown as red nodes. They cannot be visited. Other hard constraints have dependencies on previous assignments, and so we handle them dynamically by reducing the pheromone to an artificially low level. These are shown in grey. A smart function evaluator ensures we don't waste computation time by only completing evaluations of solutions that will be required for the pheromone update. This convergence plot shows the system at work, consistently minimizing the soft constraint violations over a number of reps. Our investigation into assignment order begins by generating a set of small 5 course problems and measuring how quickly the MMAS can find the optimum timetable for each of the 120 course permutations. A key result shown in the box plot is that permutation does make a difference. We observe variation as well as clusters of high and low performance depending on the ordering. In step 2 then, we train a set of regression models on these outputs and then attempt to transfer to the larger benchmark. This involves a mapping that averages the feature values over each quintile of the larger size problem perm, thereby giving us a standardized size of feature vector regardless of the number of courses. Finally, we use a simple genetic algorithm to locate a perm of high fitness, or in other words, predicted goodness. The regression model tells us the global optimum fitness we are looking for here, and therefore when it is acceptable to terminate. In our experiments, we empirically assess 10 problems from the benchmark using our predictor model as described. For comparison, we use a baseline of a random perm sampled without bias. The results show a clear split between problems based on size. At the smaller end, where problem size exceeds that of the training set by up to 11 times, consistent improvement is seen. At the larger end, the predictor fails to deliver this performance, having not captured the nuanced feature relationships we strove for. We carried out an additional experiment in which domain-specific local search operators were called to improve the solution used for update at certain iterations. We found that the more frequently local search was called, the less influence the permutation had on results across the board. In summary, the dynamic hard constraint handling procedure and partial function evaluator helped enhance a basic MMAS that found feasibility quickly on every problem tested. In our system, course lecture assignment order has an influence on solution quality that is inversely proportional to the frequency of local search operators if used. These operators, however, can be expensive when used heavily, and so practitioners may have to consider a trade-off. Our very modestly sized training set, both in cardinality and course size, was able to predict successful perms for larger problems with dissimilar structures, which is encouraging. Future work may look into expanding this set, developing a more sophisticated mapping, as well as identifying the exact point at which local search frequency renders the perm insignificant.